Alright, so let's make ourselves a goal. My goal is to project, a word we'll probably have to define, a vector B onto a vector A. So, to that end, I have here my vector A, I have here my vector B, and I want to break B into two pieces. Those two pieces are going to be a piece that runs parallel to A, like so, and a piece that runs perpendicular to A, like so. Both man left? Yes? Okay. And I'm going to kind of label some stuff, I guess. So I'm going to call this one B parallel. Call this one B perpendicular. You can color code these in your head if you want. So the vector B is going to be the sum of the two, B parallel and B perpendicular. Yes? Yep. Okay. All right. So, what do you guys think about these? What do we know that I can exploit with geometry or something here? Yeah, we could try to exploit some trigonometry. That's not a bad idea, actually. In trigonometry class, I would teach this in a slightly different way, exploiting trigonometry. As it stands, you guys have a slightly more robust tool for angles than the trig students do, which is dot products. So, I'm going to exploit dot products, right? So, I'm going to say this. I'm going to say, look, B parallel, right, is really some scalar times A. You guys with me on that? I'm going to call that scalar lowercase p for reasons.
Can I make a guess as to why it's p?
Sure.
Because it's the projection
Yep.
scalar?
Yeah, that is. So this number p is going to be a scalar, and it's going to be the projection, and it is creatively sometimes referred to as the scalar projection.
Okay. Very, very creative.
Yeah. Okay, so the way I'm going to do this is I'm going to notice, right, that if I subtract this to the other side, I've got B perpendicular, right? So I'm going to talk about taking A and dot producting with, oops, we don't need parentheses yet, with B perpendicular. That's going to be 0. Yes? So now I'm going to sub in what I know about B perpendicular. So I'm going to say I've got A dotted with, and B perpendicular is going to be regular B minus PA. So regular B minus PA. This is going to equal 0. Oops. What the hell happened there?
The zero vector.
You guys just let me get away with that?
Well, I didn't notice you did it.
It's the one-dimensional zero vector, otherwise known as a zero scalar. Okay, so I've taken this dot product. I'm going to distribute this dot product out using, well, the property of distribution of dot products, right? This thing we have. So we're going to say I've got A dotted with B minus A dotted with PA. This is going to equal the zero vector, the zero scalar. Who's with me? Okay, so now what's the unknown in this situation? P is the unknown in this situation. You guys with me?
Yeah.
So I'm going to solve for P by adding that thing to the other side. So I've got A dotted with B equals A dotted with P times A. And then you're going to use, well, you're going to use a property of dot products, right, to get that P out of there. You could also think about that as a property of matrix multiplication.
Okay, yeah.
You guys with me on that? I'm going to write this down in matrix multiplication in just a second anyway. So, if I kind of fiddle this thing out, right, I've got A dotted with B is A dotted with A times my scalar P. So I should be able to... What?
Divide the scalar to the other side. Or the A dot A.
Yeah, I can divide A dot A to the other side because categorically it's a scalar.
Yes.
You guys see that? So that's going to leave me with P equals A dotted with B over A dotted with A. You guys with me on that? Okay, so that's scalar over scalar, right? With me? Yeah. Okay. So I'm going to rewrite this just really strangely as matrix multiplication. So how do you rewrite the dot product as matrix multiplication? You guys remember that?
Dot, or matrix A.
Is it like A transpose times B?
Perfect. It's A transpose B, right? So I'm going to take the vector A, right? If I transpose it, it'll be a row,
Oh.
right? And then if I multiply that by a column B, I'll pick that column up, twist it sideways, and drop it onto my row.
Yeah.
That'll give me a 1-by-1 result, which is a scalar. You guys with me on that? On the bottom, I've got A transpose A. Everybody with me?
Yes.
Okay, so the component B parallel, right, is that P times A. All with me? So B parallel is P, this P, times the vector A. Now I'm going to do something just a little bit screwy here for reasons. Now, this is my vector P times, or sorry, this is my vector A times my scalar P, right?
Mm-hmm.
And earlier I said that B parallel is some scalar times A, right? Does it matter which side you multiply the scalar on?
Probably.
No. But that's a good instinct, right? Probably is a good instinct to have here. We should probably check. We could go back and take this out of properties of scalar multiplication that you can multiply on either side.
It's just so used to matrix multiplication. It's just...
Yeah, and you should be. Like, you should be skeptical of these frickin' things. Like, don't pretend the order doesn't matter in here, because most of the time it does. In this case, because I have a scalar times a vector, I can say that a scalar times a vector is the same thing as a vector times the same scalar. You see that? Okay, so the reason that I wrote this kind of screwy way is I'm going to rewrite this as A transpose divided by A transpose A all times the vector B. You guys see that? And then I should have to check, right, that makes sense. You guys with me?
Are you just nudging vector B up?
Yeah, I just kind of nudged A up onto the top and dropped B down. And you all should be like, no, dudes. Like, really? Does that still make sense categorically? So let me I need to be sure that A transpose is defined. You guys see that? Do you guys remember that one?
Sort of.
Sort of. So the one on the bottom is a dot product, right?
Yeah.
Sometimes also referred to as an inner product.
Oh, and then that's the outer product.
Yeah, the top is the outer product. So what's really weird is that you can get B parallel, right? By taking the outer product of A with itself and dividing by the inner product of A with itself. You guys see that?
Yeah.
That's kind of weird.
Kind of sus.
This thing here is so convenient. I'm going to call it P, like capital P. That's going to be the matrix that projects. You guys see that? So I might even call this PA, right? So this is the vector that, or this is the matrix that projects B's into B parallels. You guys cool with that? Okay, let's see. Oh yeah, and then I need one more thing, which is where the hell do you get B perpendicular from?
I would set it like dotted with A equals 0 and like something.
Yeah, so that's kind of what we did here, right? So we went through all this stuff. We were thinking about B perpendicular, right?
Yeah.
And then we kind of accidentally found this projection P. And then we were like, oh shit, the scalar P is how I'm going to get B parallel. So I started with B perpendicular and I accidentally found B parallel.
Put B parallel back in.
Yeah, so if I just take B parallel and put it back in over here, right?
Yeah.
B is made of the sum. So B perpendicular should be B minus B parallel, right? So it's the vector B minus B parallel. And then if I want to write this kind of matrix-wise, right? I want to think about, all right, so B perpendicular, right, is, I don't know, something times B minus, and then it's the PA matrix that I just found, right, times also B. You guys see that? What could you put here that would match the kind of category of PA?
On the identity matrix?
Yeah, you need a matrix here. Put the identity matrix there. You guys see that? Okay, so that means I could factor that out, right? So I could have I minus PA done to the vector B. So PA is the parallel projection matrix, and the identity minus PA is the perpendicular.
Oh, that's interesting.
You guys cool with this? So we're going to fiddle around with these a little bit. I want this to be kind of our starting position. You guys all good here?
Yeah.
Questions about this weirdness? Putting this in your head, this PA matrix, not a bad idea. We're gonna need something a lot like it in a hot minute. I would recommend that you actually memorize the thing we're gonna get in a minute, but having this available as a mnemonic is not a bad idea. Outer product over inner product is a bit easier to remember than the thing we're gonna get in a minute, but it's not gonna give you a surefire way to get a hold of the other thing. It's cool with that? Questions on this thing?